Hello, fellow number nerds, and I'm here to talk to you about my current mega favorite number, as it is the current trend, and I could not resist joining in. As the rules say, you have to talk about a favorite number that is bigger than a million, because most people, when they mention a favorite number, they're usually very small. So this is a chance to give some love to bigger numbers, and this is my chance to talk about one that I'm very happy exists, and maybe there could be a bigger one than that, but I'm gonna show you the process of how to get there. So, a thing I'm fascinated about are prime numbers, like most number nerds are, and a fun thing to do with all integers is to factorize them, but by definition we can't do that with primes. So what's another fun thing that we could do with them? What kind of pattern maybe we could find? Well, not so much a pattern, this is just a very simple thing, something you get taught in grade school. You just get the index of each prime. So you get a quadruplet of numbers, p, I, q, and r, which stand for the prime, its index, the quotient between its prime and index, and the remainder that comes off of it, and then you see what numbers come out of it. For example, 2 is the first prime, so it is index 1. When you divide 2 by 1, you get quotient 2 and remainder 0. And as a note, this is the only time that we're going to have remainder 0 ever. 5 is the third prime. 5 divided by 3 equals 1 with remainder 2. 11 is the fifth prime. 11 divided by 5 equals 2 with remainder 1, and so on. You can carry on with this process. You can write a good enough program to make him spit those out to you. But the point here, and this sheet is already made. I'm just gonna turn the text into black. What I'm wondering is there a quadruplet P, I, Q, and R such that they're all prime? I guess that would be a fun thing to find. And what's also nice about that is that it is a nice property that doesn't depend on base. And sure enough, you don't have to go very far to find out 3 cases, with 17 being the 7th prime, getting quotient 2 and remainder 3, and same thing for 41 and 367. So all of these numbers here are prime. So I guess you could fit them in a sequence, which I have, I'm gonna talk about it later. But then I think, how do we go on to find more numbers like these? I mean, these 3 are simple enough, and you won't find any more of them for a while, for a long while. Because what happens is p keeps growing, as it is the sequence of prime numbers. With every new step, you're going to get a larger number by a few units. I also keeps growing because it's the sequence of natural numbers. It grows by 1 unit each step. Q grows 1 unit at a time exponentially slowly. And R oscillates a lot, and Q can oscillate with it. And as such, I'm gonna just show you an example of where that's the case. Like here, if we go to this part of the number line, we get to this part where Q equals 9. And a lot of the numbers before this had Q equals 9, but then it gets to 10. Okay, so it's gonna go 10 forever. Oh, no, back to 9, and then goes to 10 briefly, and 9 for a little bit, and then 10 very, very shortly, and then 9, and then finally 10, and it goes all the way to 11, whenever that may happen. And that phenomenon may happen again. It may switch between 10 and 11 for a bit until it goes smoothly along the line. You can't really tell. It just depends on the behavior of prime numbers and the relation it has with its index when you divide one by the other. But this is what can happen. So here's the thing. I think I already spelled the number down there. Prime numbers can only be odd. The only even case is 2, so we don't bother with that right now. And on the other side, we are multiplying 2 numbers and adding another. So we're basically adding 2 numbers. But considering that the first one is odd, we don't have to worry about the odd case of it being even. So these are the 4 cases that we could get. So if p has to be odd, we could have one of these 4 scenarios. But if we want I, q, and r to also be prime, and they're not even anymore, actually a correction. There's no restriction about I and Q or R any of those being odd or even. All right, but if we want the cases where they are prime, then they have to be odd. So this case here doesn't work because I and Q would have to be even. This case here doesn't work because I had to be even. This here is just rotating its case, reflecting, I guess, where Q had to be even. But this case here is when it would work in the future. So pi as a prime has to be odd, I as a prime has to be odd, Q as a prime has to be odd, and R has to be even. But for R to be even and a prime, it has to be 2, which brings us to the fourth number in the sequence. You got it. 514,275,529. With index 27,067,133, quotient 19, remainder 2. If you want to consider this my second favorite mega number, then it's okay. It's not a fixed opinion at any point. But yes, this would be the fourth entry in the sequence. This sequence right here. 17, 41, 367, my current MegaFav number, and what comes after. You know, these numbers get exponentially harder to find. You would have to change Q to be the next prime. It would have to be 23. If you don't find any of those in 23, which you have very little chance of, go to 29. And every time you add Q by 1, you're gonna raise P to an E order of magnitude because of how they grow. They tend to be E times apart when you raise Q. And the sequence as of now currently stands at as 1328022 on OIS that I submitted. I actually can't take full credit for this number here. It was easy enough to find the first 3 ones, but the 4th one I must thank Andrew Howroyd for helping me with that. And everyone that has helped me on that sequence knows that if there is a 5th number on the sequence, it has to be greater than 10 to the power of 22. Actually, I don't know how much far it could go, but with that said, I would also like to draw an analogy to another sequence that I like, that I saw from a number file video. You might recognize this one, the why 82,000 is an extraordinary number. This one here carries the property of the smaller number you can write in bases 2 up to n. Here they're written in base 10, so 2 would be the smallest one you can written as ones and zeros only in base 2. 3 would be the smallest number you can write in bases 2 and 3 with ones and zeros only. 4 would be the smallest number you can write in bases 2, 3, and 4 with ones and zeros only. And then a sudden spike. You know, the first 3 are so easy to find. The 4th one is not as small, but it's still within our grasp of language. Not that we can easily find it, but it is a nice number that we know. 82,000, as you can see here, can be written as ones and zeros only in bases 2, 3, 4, and 5, but it fails in base 6. But in my opinion, it's impressive enough that it already made to base 5. What about the next term in the sequence? It would have to be a number that you can write in ones and zeros only in bases 2, 3, 4, 5, and 6. But as of today, there hasn't been another number that can do this up to base 5. So if it happens that someone finds a number that makes this work up to base 5, and then there is going to be the very odd chance that it works in base 6, that would be a miracle. People have already checked numbers that are thousands of digits long in base 10, huge numbers. They haven't found another example that works up to base 5. So technically it hasn't been proven that there is not another term, but if there is, it is way out there. And I'm not sure about this sequence, but the analogy I want to draw is that the first 3 terms are very easy, the 4th one gives a bit of a spike, and the 5th one seems unattainable. If someone were to find a number that continues either of these sequences, I guess you could call it my next mega favorite number. But as of now, this one stands.